Today we are having Professor Amartya Mukhopadhyay from IIT Bombay. So he's basically working on battery like alkaline battery, and he's an expert in sodium ion battery. Today he is with us. He will talk about the topic, and apart from this battery, he's involved and recipient of many awards in India, like the famous Kantiswar Bhatnagar Award from India.
No.
Yeah, and there are many things.
No. I did not get the Bhatnagar. I got Swarna Jayanti fellowship.
Yeah. So let's give him the opportunity to talk, and he'll share his research. Okay, let's enjoy the talk. Thank you, everyone.
Thanks, Manus, for the nice introduction. I hope I'm audible to. I'm sure I'm audible to all of you. I hope I'm audible to also for the online audience. Right. So, thanks for coming to my talk. So, as Manas told, I'm Amartya from IIT Bombay. Now, before I go on to the scientific content of today's talk, let me show you in brief the research activities that are going on in India when it comes to the advanced batteries. Here, I have not included any industry R&D, of course. I have included most or a good fraction of the institutes and the national laboratories. Of course, I have not included, I don't know all. So, so I have included what I am aware of. So there may be many other institutes who are doing research on the advanced batteries, but overall it shows that there are activities in most parts of the country. And again, this slide was like, I made this slide during the COVID period when not much work was getting done. So it's like 3 years old and I have not updated it. That's my laziness. Right. So we are here, Mumbai. That's the western part of the country. And the institute is IIT Bombay. And in my group at IIT Bombay, we focus on the alkali metal ion batteries, as Manish told. And he also told that of late, we are focusing a little bit more on the sodium ion battery chemistry as compared to the other chemistry. Now, so this again shows the different groups that focus on batteries in IIT Bombay. So Manas did his PhD from Professor Mitra's, jointly with Professor Mitra's group and Moinak's group here. So, and in addition to that, there are about 11 groups working on in various aspects related to batteries, from say battery materials, electrochemistry, cell development, prototype, which Sagar does a lot, or he's rather expert in prototyping. In addition to the metal ion batteries, we also have groups working on the metal air chemistry, the flow battery chemistry, then power electronics, which basically is very useful for the chargers as well as the developing the battery packs, and then we also have groups working on the recycling part, what to do when we have used the lithium-ion cells. So it basically covers various aspects related to the batteries. So it's a good institute when it comes to battery research and development. That's all I wanted. That's the take-home message. Now, coming to my group, I have already told that we do lithium ion, we do solid state, we do sodium ion. And as of now, we are focusing a bit more on the sodium ion and a bit less on the lithium ion. That also has to, partly has to do with the funding scenario in India, where sodium ion is a focus from even the national perspective. So the funding scenario is good, but not just the funding scenario. It's very interesting from a research perspective, and we believe that there a lot of development can be done for the sodium ion chemistry to take it close to the lithium ion chemistry, if not better than lithium ion chemistry. In fact, having said that, for some of the aspects, sodium ion chemistry is better than the lithium ion chemistry, and it's not related to the aspects that we usually talk about, like it's cheaper, less expensive, the sources are more widespread compared to the lithium sources. We don't need cobalt in the layer transition metal oxides. That's what I will focus on in today's talk. Not that we don't need cobalt, but some aspects. We also don't need copper as a current collector. So that goes well with the with the belief, or rather the feasibility, that the sodium ion chemistry is going to be a lot cheaper than the lithium ion chemistry. So that is one side, but that's not the reason why we should be working on sodium ion. We should be working on sodium ion because it will have some operational and safety advantages compared to the lithium ion chemistry. One of the important safety aspect is that one can store sodium ion at 0 volt. So which one cannot do with the lithium ion chemistry. So which means sodium ion is very safe for storage and transportation, unlike the lithium ion. See, most of the fire hazards that we had with the lithium ion chemistry, or with the lithium ion batteries in electric vehicles or personal devices, etc. So most of these cases have occurred when the battery was actually not in use. The vehicle was resting. It caught fire, right? But so those sort of things cannot happen with the sodium ion chemistry because you can store it as a 0 state of charge, at 0 volt. Right? So that makes it very safe compared to the lithium ion chemistry. And so what we have seen is that it can be operated over a wider temperature window from minus something to plus something as compared to the lithium ion chemistry. So that makes it very important even for the tropical and subtropical regions, because where the temperature, the ambient temperature sometimes become quite high. And also important for places where the temperature goes down below 0 degree during the winter. So these are the two operational and safety advantages of sodium ion chemistry. In addition to that, many people would not have believed maybe a few years back, but now it's like it is very well known that when it comes to fast charging, sodium ion battery is much more superior than lithium ion battery. So one can, if one is able to achieve the energy density needed for electric vehicle application, sodium ion batteries will outperform lithium ion batteries when it comes to the fast charging. So that's another advantage of sodium ion chemistry. Now, if I may quote Charlie Meng, in one of our recent meetings, she told that let's stop talking to people and saying that sodium ion battery is a cheaper alternative to lithium ion. It is not the reason we should be working on sodium ion, but we should be working on sodium ion because it has the other operational and safety advantages. So was like that from battery, from real battery experts. We are a good source of encouragement. Now, so not everything is good about sodium ion, and that is why we are here working on sodium ion. Otherwise, we would not have anything to do when it comes to this chemistry. So there are a lot of challenges. One of the challenges, as we know, lithium ion chemistry has and will have graphitic carbon as the anode material. A strong word will have, but yes, it looks like graphitic carbon will be there, probably with some silicon sprinkled. But it is graphitic carbon which is the workhorse anode material for the lithium ion chemistry. But graphitic carbon does not work as an anode material when it comes to sodium ion chemistry. So one is forced to use alternate anode materials for sodium ion chemistry. Of course, it is again an intercollision based chemistry, but the graphitic carbon has to be replaced with some other anode material when it comes to sodium ion battery. So that's the first challenge. Second challenge, cathode materials. Now, lithium ion chemistry, the cathode materials are again quite standard. So it's either the lithium NMC. Of course, people are trying to move towards higher and higher nickel content, which has its own interesting and beautiful challenges which one needs to overcome. But yeah, it is the lithium NMC and the lithium iron phosphate. These are the two standard cathode materials. And so sodium ion chemistry, the cathode material is not yet standardized. What cathode material one should be using for what kind of application, it's still open. So there are three categories. One is the polyanion, the phosphates, starting with the vanadium phosphate or fluorophosphate, which are good, but they can give us the energy density that one would get using them is quite low. And using them, one cannot reach close to the level of the lithium iron phosphate lithium chemistry, which one would like to reach for the sodium ion system. So sodium ion battery will see a widespread use when it reaches the energy density of the lithium iron phosphate based lithium ion cells. So that is the first target. So to reach that, one needs to use the layered sodium transition metal oxides. Now, why these are called layered, I'm not going into detail in this talk, but this layering comes from a cation ordering. And when one views it from a particular zone axis, it appears as a layered structure. So anyway, so like even lithium cobalt oxide or lithium NMCs are also layered lithium transition metal oxides. But then the challenge with those is that there is a cation mixing that takes place during right from the point of synthesis to the operation to the charge discharge, that the transition metal, some of the transition metals, especially nickel, which is the worst offender, sometimes manganese, they go and sit in the lithium layer, and the lithium comes and sits in the transition metal layer, which screws up the entire structure and then suppresses the lithium intercalation, deintercalation kinetics, and which is a nightmare, especially when one wants to go to high nickel containing cathodes. But to start with, that problem is not there for the sodium layer transition metal oxide. The reason being, sodium ion is much, much bigger in size than the transition metal ions. So apparently, sodium ion will like to sit in the sodium layer, transition metals will like to sit in the transition metal layer, and the cation mixing, it's always there. There is nothing like 0 or 1 in science in actual world, but the cation mixing is minimal even if it is there, right? So that's good. So one can synthesize nice layered transition metal oxide to start with, but when one is using them, that is pulling out sodium and putting back sodium in, they suffer from structural degradation, and which can be quite severe, and that leads to severe capacity fade for some of the layered sodium transition metal oxide. That is one problem with this class of material. The second problem is that they are highly hygroscopic. So if you synthesize a layered sodium transition metal oxide, fantastic, absolutely stoichiometric, phase pure, perfect cation ordered crystal structure. You leave it on this table, give it maybe a day's time, and you do the XRD, you will find that the structure has got damaged, some impurity phases have come out, some residual sodium species like sodium carbonate, sodium hydroxide have formed, and the stoichiometry is no longer the one which was synthesized. So that's because it is highly hygroscopic. So presence of moisture and carbon dioxide kills the material, completely damages the material. One day in air or a few hours in water, it's gone. So which means that handling storage of these materials is a big challenge. Yes, you can synthesize them in a nice layered structure to start with, but the handling storage is a big challenge. Unlike the lithium layer transition metal oxides, they are also hygroscopic, especially the high nickel containing ones, but not as bad as the sodium transition metal oxides. Now, so handling storage is a problem. Second, ideally, one would like to get rid of NMP for the preparation of electrode slurry, because NMP is toxic, hazardous, it can cause a lot of different problems. So one would like to use water to make a electrode slurry, but then if these are so hygroscopic, if you cannot even leave it in the air for more than a day, or cannot dip it in water for more than a few hours or even minutes, you cannot prepare an aqueous slurry with these materials. So then one has to improve the air water stability of this layered sodium transition metal oxide cathode material. So overall, the suitable electrodes need to be finalized for the sodium ion chemistry, and also the electrolyte plays a very important role. The selection of the right electrolyte and the right electrolyte additive plays a very important part in the stability of the sodium ion chemistry. Right? So that's like a kind of overview. Now a quick look at so this shows that it is expected that sodium ion batteries will be 30 to 40% cheaper, which I've already told. Now, if one looks at some of the commercial level prototypes that came into the news, so and a few couple from India, there are more to due to be commercialized in India by some of the firms. Now, if one looks at the cathode materials here, one can. So if you recollect, I told that to reach the energy density of the lithium iron phosphate lithium ion cells, one has to use layered sodium transition metal oxide, but that is not what one sees here for many of them. So some are using the Prussian white, Prussian blue, some will be using the sodium vanadium phosphate. Not all are using the layered sodium transition. KPIT is using layered sodium transition metal oxide for their high energy density cells. But for the lower energy density cells, they are using the sodium vanadium phosphate, some variant of Okay, so which again tells that there are certain challenges with this layered sodium transition metal oxide, and that is what I was talking about a few minutes back. Now, what are these layered sodium transition metal oxide? These appear like this when you look at it, kind of a view from the side. Right? Now, the O3, what you see here, it's basically the lithium cobalt oxide structure. Here, the O stands for sodium ions occupying the octahedral sites or coordinated in an octahedral manner by the oxygen ions. Now, when it says P, it means that sodium ions are taking up a trigonal prismatic site. So that's where the terminology P comes into the code. Sodium ions, when bigger than lithium ions, can take up prismatic in addition to octahedral sites, whereas lithium ions can take up octahedral and tetrahedral sites. Lithium ions can't take up prismatic sites. So now, because sodium ions can take up octahedral as well as prismatic site, it leads to different structural types for the layered sodium transition metal oxide. Now, the reason we call it layered is because something to point right. So the reason it's called layered is because these green balls, they represent sodium ions. They appear to be in one layer, and what you see here, these represent the transition metal ions, kind of another layer. And the transition metal ions as well as the sodium ions are coordinated by the oxygen ions, which are shown as red dots. So now, coming to the two structure types, or the O type as well as the P type structure. For the O3 type structure or the O type structure, the sodium ions are taking up octahedral coordination by the oxygen ions. The sodium transport is a bit sluggish because during the transport, sodium ions have to move from one octahedral site to an adjacent tetrahedral site and then to the octahedral site, and so it moves like this. It's sluggish. In prismatic coordination, the sodium transport is very fast, much facile, because it can move from one prismatic site to the next prismatic site. So it's quite fast. So when we talk about fast charging, this type of cathode material which are ideal for fast charging, and it can lead to a very high rate capability. Now, but the problem with this P-type structure is when you synthesize the material, you cannot have a starting sodium content of beyond 0.7 per formula unit, usually. So that's a big challenge. Now, in any alkali metal ion cell like the lithium ion, sodium ion, calcium ion, whatever, it is the cathode material which is the reservoir for the alkali metal or the alkali earth metal ion, right? So now, if your cathode material starts off with a low alkali metal ion content, it's not good for the cell. Even balancing the cathode anode capacity becomes a problem because during the discharging, the sodium content may go beyond the starting sodium content and which can. So ideally, what I would like to have the sodium content 1 per formula unit, if not at least more than 0.8, 0.85, at least more than 0.7. So that is one challenge when it comes to the P-type structure. I will be towards the end of my presentation. I will show a couple of slides or 2-3 slides on that. Now, for both of these, the air-water stability or the air-water instability is a major problem. So the first part of the talk will focus on the air-water instability based on how to address the air-water instability based on a few model O3 structured cathode materials. So let's move ahead. Okay, while I'm showing this slide, just wanted to point out a beautiful aspect of these structure types, which is basically which will be the basis of what I discuss in the slide. So this is very important. Now, when we see the oxygen ion, it is the same oxygen ion which is bonded to the sodium ion on one side, and the same oxygen ion is bonded also to the transition metal ion on the other side. Now, sodium oxygen bond, as we know, is predominantly ionic bond. So not much can be done to the character of the bond, I suppose. It's an ionic bond. Whereas the oxygen transition metal bond, the transition metal oxygen bond, it's an iono-covalent bond. So by varying the degree of covalency of the transition metal oxygen bond, a lot can be done to the character of the bond. One can polarize the electron cloud towards the oxygen ions, away from the oxygen ions. and change the length, strength of this transition metal oxygen bond. That's high school chemistry. Now, I just take back what I said a few seconds back, that nothing can be done to the oxygen sodium bond because it's a predominantly ionic bond. But I take back that statement because this oxygen ion is also bonded to this transition metal ion, and one can play with the covalency of this transition metal oxygen bond by selecting a suitable cation here. If one does that, one can tune the effective negative charge on the oxygen ion. And if one can tune the effective negative charge on the oxygen ion -2, -1.9, -1.8, -1.7, whatever, then one can, of course, simultaneously tune the strength and the length of the sodium oxygen bond. Right? So, which means in this structure, the character of the sodium oxygen bond can be tuned. And that is what one can use to the advantage while improving the air water stability as well as designing high sodium containing ethyl. So how we will see now. Right. So this, I think we have discussed this. This shows some of the problems associated with layer transition metal oxides. So too much of structural transformations as indicated by these plateaus during the charge and discharge leads to structural instability. There are other transformations like sodium vacancy ordering in these layer transition metal oxides detrimental to the structure. Then there can be Jahn-Taylor distortion if you have some Jahn-Taylor active ions. Then there can be transition metal dissolution, very bad. Then air water instability. So here it causes leads to a challenge for handling storage as well as kind of mandates the usage of NMP as the medium for preparing the electrode, which one does not want. One wants to do away with NMP and use water to prepare the electrode. Absolutely. Cost effective and environment health friendly. So let's look at how to address these two. Okay. So this is the concept which I will be using for the entire talk from now. And let me again just recap that this oxygen ion is bonded to sodium ion on one side, ionic bond, transition metal ion on the other side, ionocovalent bond. So now, if this bond is more covalent, my electron cloud will be polarized away from the oxygen ion more towards the center of the bond. Whereas if this bond is less covalent, more ionic in nature, then my electron cloud will be polarized more towards the oxygen ion. Now, in such a situation where this is a little bit more ionic, has a greater ionic character, because my electron cloud is polarized more towards oxygen ion, it increases the effective negative charge on the oxygen ion, which will render this oxygen sodium bond, which is predominantly electrostatic, stronger and shorter. Now, if that becomes stronger and shorter, it will suppress spontaneous sodium removal from the lattice. And why is that important? Because the starting point of the air water instability is spontaneous sodium removal from the lattice and simultaneous insertion of H plus or H3O plus into the lattice. So if I can suppress the initiation of the instability caused upon exposure to air or water, which is the spontaneous sodium extraction, by making the sodium oxygen bond stronger and shorter, I will do a good job in improving the air water state. So now the way forward here is to design layered sodium transition metal oxides, which will lead to which will impart a little more ionic character to my transition bond. And the way one can, so the descriptor of the design criteria can be, if I can have cations in my transition metal stack, which will have a lower charge density. And that can be achieved by having a lower charge to size ratio of my transition metal ion. A lower charge to size ratio indicates a lower charge density on the surface of the transition metal ion, which indicates that the electronegativity of the transition metal ion is lower. It will have a less affinity for electron, which indicates that it will make my transition metal oxygen bond a little bit more ion compared to the reverse scenario. So that is why throughout this presentation, I will use this descriptor charge to size ratio. C is to S, which is basically indicating the ratio of the oxidation state and the ionic radius of the cation, which basically, in simple terms, the higher the charge to size ratio, the greater will be the covalency of my transition metal oxygen bond. The lower the charge to size ratio, it will be moving towards this situation where the degree of covalency is lower for my transition metal oxygen bond. Again, that's nothing more than a high school chemistry. Okay, so if I develop a layer transition metal oxide with my transition metal layer having a lower charge to size ratio, I will end up making the sodium oxygen bond stronger because of the polarization of electron cloud more towards the oxygen ion, and so sodium ions will feel difficult to spontaneously come out from the lattice. And at the end, I will see whether I can use the similar concept of charge to size ratio to develop high sodium containing p-type structure. So if we are all on the same page, let's move forward. So to test the first hypothesis, that if by lowering charge to size ratio of my cation combination in my transition metal layer, so this is what I mean by my cation combination in my transition metal layer. If by lowering the charge to size ratio, can I improve the air-water stability? So based on my hypothesis, this should give me the lowest charge to size ratio bearing cathode material should give me the best air-water stability, and this should be the worst of the lot. Okay. So now, if I look at the structure, I can see that it agrees with my hypothesis in the sense that when I have a low charge to size ratio, my inter-slab spacing. So this is my inter-slab spacing in the battery. Like the battery community, when one looks at this layer transition metal oxide, one refers to that transition metal oxygen as slab, and the alkali metal ion layer as interslab. So as if between the two slabs. So when I say interslab spacing, I mean the sodium layer. So as I lower the charge to size ratio of the cation combination in the transition metal layer, my interslab spacing goes down, which indicates that my sodium oxygen bond has become smaller and stronger, and sodium ions will not find it easy to spontaneously come out of the lattice. So this one should give me the best air-water stability. Now, DFT calculations by my colleague Abhijit Chatterjee in IIT Bombay. So so the calculations also show that is also in sync with what we thought. So when we have lower charge to size ratio, so the effective negative charge on the oxygen ion is more negative. So which means it will make my sodium oxygen bond stronger, as we had expected. Now let's move ahead. Let's see the results. So the one on the top are excites taken after different intervals of air exposure. One can see for the cathode material having the highest charge to size ratio, even after 15 minutes of exposure in air, it has started forming the impurity phases and the structure has started changing. So it's highly unstable in air. By contrast, for the material having the lowest charge to size ratio among all, it's stable even after 40 days of air exposure. No change at all can be seen from the excited. The similar sequence of events when we dip it in water, just that it is faster. So after 3 hours, the structure is completely gone. Soak for 12 hours, it's gone. For this one, with a high charge to size ratio of my cation combination in the transition metal layer, whereas this is again not just air stable but also water stable. If we look at the TM image after water soaking for 12 hours, as expected, the structure looks totally damaged, whereas this looks perfectly intact, as if it was just in the side. But no, it was soaked in water for 12 hours, then the TM was done, and it looks perfectly intact. So it kind of proves the hypothesis that when we have a low charge to size ratio of my cation combination in the transition metal layer, the air-water stability is much better compared to the other way around. And so like we had made, I think, 6 materials. The materials with the intermediate charge to size ratio follow suit. So I cannot show everything in the publication, but in the slides, but it's there in the paper if one wants to have a look. Now coming to the electrochemical behavior after soaking in water, the high charge to size ratio bearing one shows a near complete degradation. I mean, it does not cycle after it's soaked in water. As simple as that. No need to elaborate further. And the impedance is very high after soaking in water. But the one with the lowest charge to size ratio hardly shows any difference in the electrical behavior before and after water. And neither has the impedance increased. Then, as I told, the one with the intermediate charge to size ratio follows suit when it comes to the degradation of the first cycle capacity after water soaking. So this is perfect. This is very bad, and the increment in the impedance after water. Now, point to note here is that it is the charge transfer resistance which increases drastically, which means that it is not just the formation of the surface residual species, but the damage done to the structure, which is highly significant, especially for these transition metal oxides, where the charge to size ratio is very high and which are highly unstable when soaked in water. So that kind of proves the hypothesis, and it kind of gives a descriptor that okay, by selecting or by engineering the cation combination in my transition metal layer of this layer, sodium transition metal oxides, I can improve the air water stability to a significant extent, and which will be very important for a practical usage. And this charge to size ratio can be a good descriptor for the same. Now, moving ahead, this all that I show in this slide has nothing to do with air water stability. The materials, all the materials for this part of the study were synthesized and stored nicely inside the glove box, absolutely well protected. So they're not exposed to air. Still, what we see is that the cathode material with the lowest charge to size ratio shows much better cyclic stability as compared to the material with the high charge to size ratio. Again, there has been no air or water exposure to any of them. Still, the low charge to size ratio is not just good, not just for the air water stability, but also for the electrochemical cyclic stability. Why? We will see now. Okay, so this shows that as the charge to size ratio, the transition metal layer goes down, my cyclic stability increases for all the materials. So when we did the in situ XRD, what we figured out was the one with the highest charge to size ratio underwent all possible structural transformations during charging, and no wonder the structure was totally unstable. The structure got damaged during the cycling and it showed a drastic capacity. By contrast, the one with the lowest charge to size ratio bearing transition metal layer, it showed just one O3 to P3, which is known to be a reversible transformation during the entire charge and discharge. Whereas this one had undergone multiple transformations, all possible transformations. And the ones with intermediate charge to size ratio followed suit. So DQDB also shows that with the lower charge to size ratio, the potential for the first transformation moves to a higher value, to a higher potential, which means we can extract more sodium before it initiates the first structural transformation, as the charge to size ratio is lower. Now, from our in situ XRD, we figured out that there seems to be a kind of critical ratio between the interslab spacing to the slab thickness at which the O3 to P3 structural transformation gets initiated. So if the initial ratio is much lower, as with the low charge to size ratio containing material, then a lot more sodium can be pulled out before it hits this critical ratio and the structural transformation. Whereas pulling out a little bit of sodium from this will lead to initiation of the first transformation, and no wonder it will undergo all the transformations and it will get damaged very fast. Right? So yeah, so that's what it is. Now so this shows just one example of an aqueous process layer transition. So this material was highly water stable. It's very much water stable. So one could make the cathode using water as the medium, not NMP, and it cycles reasonably well. Of course, one has to make it more stable. So this is an example of, I think, full cell, forget it. Yeah. Now, one thing which must have come to the mind for all of you, that the way I'm improving the air water stability is by making it more difficult for the sodium ions to spontaneously come out of the lattice, which means I am suppressing to some extent the sodium transport, making it less facile. I'm lowering the kinetics. So that should negatively affect my rate capability. And that is indeed so. Just that the rate capability is not very badly affected by slight alteration of the charge to size ratio. Rather, it is the spontaneous sodium extraction which is more drastically affected. But having said that, I don't want to compromise on my rate capability as well. So again, going back a little. So now this on the left hand side is the composition, which was absolutely water stable, using which I had shown the aqueous process cathode. It was perfectly water stable. But then the rate capability was not that great, understandably. So we tweaked it a little bit. In place of titanium, we replaced a little bit of titanium, just a little bit, with silicon. Both 4+, but silicon has a greater charge to size ratio, greater covalency, which made my transition metal oxygen bond a little less ionic compared to this one. Or it dilated my sodium interslab spacing just a little bit, so that it did not negatively affect the air water stability, but it improved the rate capability in significant and by improving the sodium diffusivity. So this descriptor of charge to size ratio can be used to improve the air water stability, as we have discussed, and it can by tweaking it very thoroughly, or by being very careful, one can also use it to improve the rate capability without negatively affecting the air water stability. So that is very much possible. Right, coming to the last part of the talk, high sodium containing P2 structure. So just as a recap, the p-type structures with the sodium ions occupying the prismatic side is very important, because it can lead to very high rate capability, that is fast charging capability. But the problem is the p-type structures form with a low initial sodium content of usually less than 0.7 per formula unit. A classical composition is Na 0.67, as low as that. Okay. So now, if we want to have the prismatic coordination stable, that is P2 type structure stable with higher sodium content, the best thing to do is first having a close look at the octahedral versus prismatic coordination. So that is what it shows here. This is my octahedral coordination, this is my prismatic coordination. What I can see here is that for the octahedral coordination, my oxygen ions are not directly one on top of the other. They are not residing directly one on top of the other. They are slightly, so it's like slightly slanted. The center lies a bit away from the center of the bottom one. Whereas for the prismatic coordination, they lie directly on one on top of the other. That's the geometry of the coordination. We cannot do it. So this indicates that from this one can get an idea that, okay, if my oxygen ions can have slightly lower effective negative charge, then they might like to reside one on top of the other, that is maintain a prismatic coordination, even if I stuff more sodium ions in between them, and so that because of which they come closer to each other. So here the idea is just the reverse of the previous thing. The idea is to lower the effective negative charge on the oxygen ion. And how can we do that? Now by increasing the charge to size ratio, or selecting a cation combination in my transition metal layer with a higher charge to size ratio. That will lower my effective negative charge on the oxygen ion, because it makes my the transition metal oxygen bond a bit more covalent, and the electron cloud is polarized a bit away from the oxygen ion. Now, when we looked at the lot of P2 structured material reported in the literature, we could actually segregate them into two domains based on the charge to size ratio of the cation combination in the transition metal. So those having a lower charge to size ratio fall in the O3 domain. These are all O3 structured, and with the higher charge to size ratio for a given sodium content, these are all P2 structured materials. And in fact, one can draw a line separating these two domains, and one can get an equation for the line. So one can know that, okay, if I am on this side of the line, if I want a sodium content of this, say 0.9, I need to have a charge to size ratio of 6 or more to be on this side of the line. If I have it lower than that, I will be lying on the O3 domain. So based on this, we designed two compositions, one with the charge to size ratio falling in this domain, and the other with the charge to size ratio falling in the O3 domain. All we did here is replace, either have manganese 4+ or titanium 4+, same amount with everything else remaining the same. And indeed, we saw that this having a lower charge to size ratio crystallized in O3 structure, this having a higher charge to size ratio crystallized in the P2 structure under exactly the same condition. And again, DFT showed that, as expected, this had a greater effective negative charge on the oxygen ion, so it would not like to adapt this coordination, it adapted this coordination, and the other way around for this. Now again, one cannot simply design a high charge to size ratio containing or a transition metal layer with a high charge to size ratio, because, and at the same time keep increasing the sodium content, because charge neutrality has to be taken into account. While on the transition metal layer, one is increasing the charge, one cannot keep increasing the sodium content. That also has a positive charge, right? So then there will be a compromise based on the required charge to size ratio for adapting the P2 type structure, and the allowable charge to size ratio based on the charge neutrality. So while trying to design compositions, one will all face this compromise, and one will narrow down to a particular composition which seems feasible based on this composition. So this is where we were for this material, and as I will show here, it formed a perfect P2 type structure, phase pure, with a starting sodium content of 0.84, much better than the typical 0.67 per formula unit. And no doubt, it exhibited a very good first cycle reversible capacity, probably more than most other P2 structured materials reported in the literature. What I'm showing here today is between 2 to 4 volt. I'm not talking about what will happen if I go beyond 4 volt. And within the 2 to 4 volt, the cyclic stability was very good, even at a high current density of 2.5 C. It does not seem to fade at all. So it's a very nice cathode material, right? And so since we had stuffed more sodium, the interslab spacing had got a bit narrower. Again, going with the same logic, the air-water stability is very good. So this one is water soaked, this one is protected in glove box, and both show the same electrochemical performance as a cathode material. Right? So this is a full cell with one of the laboratory made mushroom derived carbon, not really a good hard carbon, but yeah, in a full cell configuration, it is also quite good. Now, so coming to the end of my talk, I hope I have been able to convince you a couple of things. One, by playing with the charge to size ratio of the cation combination in the transition metal layer of layered sodium transition metal oxide, one can improve the air water stability as well as the electrochemical cyclic stability in significant terms. One can also tune it a little bit on the other side to improve the rate capability, and by using the same logic, one can make the prismatic coordination more stable at a higher sodium content, thus develop a high sodium containing P2 structure, layered sodium transition metal oxide. With this, let me come to the end of my talk, and let me thank my funding agencies, my collaborators, and the students who did the work. I did not do the work. It was the students who did the work. I'm just presenting on behalf of them. So the major contribution for this work was from Bachu Shravan Kumar. In fact, this is his PhD thesis presentation, to be very honest. So Bachu Shravan Kumar, who is now in MIT, USA for pursuing his postdoctoral studies, he got some help from Anagha Pradeep, another PhD student, whose topic was a bit different. She was working on sodium titanate-based anodes, but they collaborated, which is always good to do. And so I thank Anagha Pradeep. So Anagha has submitted the thesis. The defense is yet to be done, but she has joined Reliance India as a battery scientist. Ishita was a master student who contributed in the high rate capability, achieving high rate capability, as I showed. And so she was working as a battery scientist in KPIT Pune, the firm which commercialized India's first sodium-ion cell. And now she has got a PhD position somewhere in Sweden. I just forgot. So she will move there. And with this, let me thank all of you for the patient hearing today. And I can take up any question, any discussion, related, unrelated, it's all fine. So thank you very much. The point by summary.
Thank you, Professor, for such a nice informative talk. I think we all enjoyed it really. So do you have any questions? You can see from the audience part.
Hello. Thank you very much, Professor. That was a fantastic talk. Really well polished, and all the questions I had, you ended up answering as they went on. So that was really good. So I have to thought of a bit of a weird one. You obviously there are fantastic benefits associated with being able to water process an electrode rather than have to use NMP. And one of those is the health and safety. I think you were using it. Was it a sodium alginate you were using as the binder in the water brace?
So we typically use sodium alginate as the binder in our lab, but we have also done CMC SBR. But usually we use sodium alginate. Yeah.
I suppose this is, again, you pretty much answered everything. I was just wondering, with the water stability, do you think that there would be any effect with pH, depending on if you're using a binder that might alter the pH of the system?
That's a very good question. So that is something which people are looking at it. I don't have a yes or no answer right now. All I can say that it is expected to affect, right? Because see, pH means it's the H plus activity at the end, and that is the Na plus H plus exchange is the starting point of the sodium, the water instability. So yeah, so depending on the pH, the H plus activity, I'm sure it will have a lot of influence, but that is not very well known what kind of influence it has as of now. Right? But that's a very good question, and that's the thing to look into.
Fantastic. Thank you again. That was brilliant.
Declan, so is yes.
I think the online audience, because we can hear each other.
Okay, thank you again for very fantastic talk. And I agree with Declan that you answered all questions we had in the next slide. But because my background in physics, I'm not working in battery, but I'm really interested. Yeah, I'm really interested in your whatever you explained about the the origin of the bonds of sodium with this kind of hosts. And you mentioned that you are playing with the electronegativity of the transition metal to tune the strength of the bonds. And then the question was how the rate capability and the charging, discharging affecting, of course, is more stable. So you use the dopants to address that issue. My question is there any study regarding the density of states on the oxygen point that's affecting the strength of the bonds without the dopants, and how it's dependent on the kind of dopant? For example, you tried something other than Si, and how the density of a state is changing there.
Perfect. No, that is something we have not looked at in detail. All that was looked at was the Bader charge analysis. So that was done. So that gave us the effective negative charge. But then the density of states was something which was not looked at. But I'm sure the density of states will differ and that will have an effect. But yeah, that was not looked at. That's a DFT calculation. So I can request Abhijit Chatterjee to run some more calculation to answer this question. But yeah, as of now, it was not done.
And you tried any other dopants instead of Si?
Not for that purpose, no.
Okay. But because it's very fantastic.
The is a bit different. I understand where this question is coming from. Yeah, it's quite different. It's not a transition plan anyway. Right? So
But
the density of states can matter. Just that the observations kind of agreed with each other, like the interslab spacing slightly got enhanced and the rate capability increased, and based on our hypothesis, we expected the interslab spacing to get enlarged a bit. So it all tied up, but yeah, density of states is a good thing to do, especially for that part. I agree.
Yeah, a very smart solution for that rate capability using dopant.
Thank you, Naima. Is there any question? Yeah.
Thank you. It was really a very, very interesting talk. I have one question, which is not in the sodium ion area, but you have this fantastic understanding of, how you changed your transition metal and oxygen bond with your size to charge ratio. Have you ever thought about using some of these materials for, say, oxygen evolution reaction and oxygen reduction reaction? Because now you are basically changing the, the ionic strength of your oxygen in your with the cations.
Right. No, because I have never done catalysis, so I have not tried that. But yeah, so maybe we can discuss more about that. And
yeah,
I'm sure
because that is very interesting. So it's very tunable, it seems, and so it is. The chemistry was very tunable, and I was just wondering that if you thought about it.
Yeah, no, that's a very good idea. But unfortunately, I don't do catalysis. But if I have a collaborator, I mean, it will work. Yeah, I know. Yeah, that's right.
Thank you, Parama. Peter.
Thank you, Professor. That was a really, I have to say, fascinating talk. I have a question about the tuning of covalency and therefore the interslab spacing, and you use titanium as candidate material. Are there any other candidates which may be as good, if not better, than titanium?
Yeah, so titanium was so what we were trying to do, we were just trying to keep it simple. The reason titanium was invoked here was because both have a +4 charge. Similarly, silicon, the reason it was picked up was it has a +4 charge with a very low ionic radius. So titanium, manganese both lie in the 3D period. So both are transition metal ions and 3D transition metal ions. Now, so both have +4 charge, and so for this particular composition, even manganese will adopt the +4, titanium will adopt +4, and they have a different ionic radius. So that's why titanium was chosen. But not all our compositions have titanium. So titanium was used to primarily explain, but not all compositions have titanium. This one does not have titanium. A majority of them have. This also does not have titanium as such. But so it was more about varying the charge to size ratio in a systematic manner rather than focusing on one particular transition metal.
Thank you.
Thank you.
Thank you, Peter. Thank you, Professor. So maybe we can have a look online. So we have, no questions. So, and if anyone having any more questions, they are welcome to reach Professor through the email. And a big thank to Professor now from all of us.
Thanks.
So really, we enjoyed the talk. Thank you so much.